In this problem, we're asked which of the locations is going to be most likely abstracted when you're treating it with sodium hydride or sodium hydrogen, right? So we're going to add a sodium and a hydrogen. Well, sodium is always positive, and sodium hydrogen is going to be like neutral. So if sodium is positive, then our hydrogen has to be negative, which isn't really common. It's pretty bad for this, right? But the main thing that you need to know is what is abstraction. So abstraction is when a hydrogen acts as a free radical. So hydrogen is going to have this electron with it, and it's going to want to try to rip off another hydrogen. And if we have a hydrogen, right, that has a dot, then they can actually connect, right? So these two electrons are going to meet together and they're going to form, and they actually form the naturally occurring element of hydrogen. So these two radicals will form to make H2. Therefore, this little one is going to want to try to rip off a hydrogen so it can become H2. Alright, so which one is more likely to give up its hydrogen? That's what the question's asking. Which one is most likely to be abstracted? Which one is most likely to give up its hydrogen? Well, you should know that as the acidity increases, the abstraction rate increases. Because if you're more acidic, then you're most likely to give up your hydrogen, right? And if you give up that hydrogen, it's going to be abstracted. So the more acidic you are, the most likely you are to, to be abstracted. So really this question is an acid question. It's asking you which part of the molecule is most acidic. Alright, now that we know what we're asked, we can verify this, right? So recall that as SP character, right? So the more S you have, this one is going to have a 50% S. There's only two things. One of those things is an S, right? So it's 50% S. And that's really good for acidity, because notice that we only have carbons and hydrogens, right? Well, if you only have carbons and hydrogens, you're going to be using the SP trend. Sure, you can do pKa as well, and I highly recommend this. The trick that I'm using doesn't work a lot of the times. Like, it works most of the times, but there are times where it doesn't work, and I'll show you those times in these videos, right? So when you're dealing with carbon and hydrogens, just use the SP trick. So an SP2 is going to have three things. There's one S and then two P's. That's where we get from over there, right? So that's 33% S, and then SP3 is going to be 25% S. So as you can see, the more S character you have, the more acidic you become. Well, let's look at this area, okay? Let's look at that area. Well, it says that there's a carbon with another carbon, and there's a carbon. This one's going to have a hydrogen. It's connected to a carbon. Alright, so 10, 8, and 7. Well, let's see. For 8 we have 1, 2, 3, and 4. So for 8 we have 4 things surrounding us. That makes us an sp3. S1, P3, 1 plus 3 is equal to 4. So number 8, it has 4, it's sp3 hybridized. That means it only has 25% S character, which makes it very, very, very basic. It's not acidic. The less acidic you are, the more basic you are, okay? So as acidity decreases, basicity, the more basicness you have, increases. Alright. Likewise, there's an H over here, an H, and an H right there. It's going to be the same thing for number 9. That's a 9. That's a 9. So for 10, 8, and 9, they're all sp3. And so they're not acidic. Since they're not acidic, they're not going to want to give up their hydrogens, right? So that's a really really bad location for our free radical to go to. Alright, so let's see 6 and 5. For number 6, we have C, C, double bond with another C. 1, 2, 3, 4. Okay, this has 3 hydrogens, and we're only focusing on, let's do this, right? 1, 2, 3, 4. Alright, so let's see here. 1, 2, and 3. There's 3 things, because carbon always wants 4 bonds. We already have 4 bonds, 1, 2, 3, and 4. So there are 3 things surrounding us in this carbon 6. And if there's 3 things, it's going to be sp2, because 1 plus 2 is equal to 3. And sp2 is going to have 33% S character. So this is more acidic, but it's not the best location, right? It's not that acidic. It has an acidity or a pKa of around 44, right? So keep in mind this is going to be 25. You should know your pKa's, 25, 44, and 50, right? This is for carbon and hydrogen bonding. So 44 is not that good. If anything, out of this whole molecule, I want something that gives me 25 pKa. Because the less pKa you have, the more acidic you are. Alright, so let's go to 1, 2, and 3. We have carbon with a carbon that's triply bonded to a carbon, right? And we have some hydrogens. Let's see here. Okay. Alright, well, I know for sure carbon number 3 is not going to be acidic because, well, actually it shouldn't be there. Okay. I know that carbon number 3 is not going to be acidic. It's going to be like sp3 hybridized. You have a hydrogen and a hydrogen there, so it's going to be sp3, not good. But notice that this carbon right here, it only has 2 things attached to it. 1 and 2. And because it only has 2 electron zones, you could call that, it's going to be sp, because 1 plus 1 is 2. 2 electron zones. Alright, so since it's sp, notice that it's linear, right? Linear. Usually triple bonded is sp for carbon and hydrogens. Since it's sp, it's going to have 50% S character, and since it has 50% S character, it's more acidic. In fact, it has a pKa of 25. And since it is more acidic, it's more willing to give up that hydrogen. And that hydrogen is going to break off. So we get these 2 electrons. And then it's going to merge. With this hydrogen right there. And together they're going to make H2. So really this question is testing you for your sp character trends, your pKa for carbon and hydrogen, and abstraction. It just means that hydrogen, this lone hydrogen, is going to try to snatch another hydrogen from this molecule and combine with it to make H2, which is a more stable product. Alright, hopefully this helps you. Alright, so this is like a mixture of pKa and trends, the way I look at it. Well, which one is the most, well, going from 1 through 5, 1 being the highest and 5 being the lowest, or, I mean, we're going to rank these, right? We're going to rank these. So, we're going to rank them from most acidic to least acidic, right? Okay. Well, the first thing I want to do on this problem is realize that oxygen is going to be the most electronegative and thus more acidic, because as electronegativity increases, acidity tends to increase as well. So for sure, I'm not going to pick 1, 3, or 5 for my first answer. And since I'm not picking them, A, D, and E can be incorrect. We can cross them out. Alright? So knowing this, you're probably wondering, well, Brian, why is number 2 more than 4? I thought we were looking at bonds, right? The more bonds you have, the more stable you are. Well, that is true, and that tends to work. But you have to realize that oxygen typically wants 2 bonds, right? It always wants 2 bonds. If it has 3, that's okay, but it's not the best, right? Like you want to go to Cheesecake Factory, but you end up going to, well, Olive Garden or something, and you're like, oh, this is okay. I could have settled for Red Lobster, or I really wanted to go to the Cheesecake Factory, but I guess I'll be here, right? That's what oxygen is doing. Oxygen really likes to have 2 bonds. And you're probably wondering, well, this one doesn't have 2 bonds. What's up with that? It has 3, and this one has 4. Well, you have to think anion, right? So we have oxygen. This oxygen has donated a hydrogen, right? It has donated a hydrogen, and so we're now that's positive. We have 2, 4, 6, and 8. So that hydrogen left, so we're going to have our electrons being put on the oxygen, right? So that those electrons broke, and they shifted to the oxygen, right? That bond broke and shifted to the oxygen. And so oxygen likes to have 2 bonds. In fact, one thing that is very important for you to know is that water can only produce 2 things. Water can give you OH, that's the strongest base possible in water, and hydronium, and that's the strongest acid, right, in water. Okay. When we donated this hydrogen, oxygen got 2 bonds, and that's always positive. That's always good for oxygen. And since it's very, very happy, it's going to be acidic. So we can say 2 is going to be very acidic because oxygen always wants 2 bonds, right? And it doesn't matter. It doesn't matter that this is a carbon and this is a carbon as well. It's the format. Oxygen has 3 things attached to it, and it's positive. Do you see that? We have 1, 2, 3 things attached to it, and it's positive. This can be whatever on the exam, but if you see oxygen attached to 3 things, one of them being a hydrogen, and it's positive, you can say, hey, if that hydrogen were to pop off, well, oxygen's going to have 2 bonds. It's going to be neutral, and it's going to be super acidic. So you can say that. pKa for hydronium is like negative 1.7, right? Okay. So it's negative 1.7. Alright. And you have to realize that when oxygen comes off of this molecule, you'll have this right here. And an oxygen with a negative charge. Well, that oxygen doesn't like having just 1 bond. It likes to have 2 bonds. So of course you can like shift some electrons over there, but then you have to do this, right? You have to do that, and like this bond travels somewhere else. It becomes a mess, right? So you have to realize the trend for this. You have to realize that oxygen loves to have 2 bonds naturally. It doesn't like doing any shifting. It doesn't like to do any moving. It likes to have things handed to it. And then you have to realize that oxygen itself is pretty negative. So even if number 2 is correct, we're going to have number 4 following it. Because of both oxygens, it makes them acidic. Acidic, right? Okay. Now, the one that's like super controversial in this problem is either going to be 1 or 5 or 1, right? So it's either 1 or 5. Well, if you knew pKa, and I highly recommend that you learn it, this is going to have a SP character of 50%. Turns out that this is 25. Ammonia is going to be what? 38. So it's going to be 1, 5. And finally, the last one is 3. Okay. I mean, it seems very counterintuitive. You would expect that nitrogen would be more electronegative, and therefore it would be more acidic, right? But, I mean, sometimes it doesn't work. Like, if you ever come in this type of question on the exam, if it comes up, I highly recommend that you just memorize your pKa, memorize some of the trends, because it's going to be real borderline, right? The pKa trick, or the trend trick, only works when you're just gonna kind of rush through some questions, and the pKa is there to actually verify your guessing, okay? So it's there for verification. So pKa is like the last resort you have for these types of questions. And for 3, it's a double bond, and double bond typically has a pKa of 44 because it has an sp character of around 33%, right? So, I mean, it's pretty easy. Triple is 25, double is 44, and then single is 50, right? So that's for carbon and hydrogens. And ammonia, you're just gonna have to know that, right? Sorry about that, but it happens. Okay, so we have this practice problem, and I wanted to go over the acid and base reactions, because I noticed that a lot of the students were having some trouble just figuring out how to think about these types of problems and which reaction side would be preferred, right? So this whole section is going to be about how to do those problems with and without the pKa. And I strongly kind of lean towards the without pKa because it's really just trends. And you can use the pKa to verify, okay? But if you really want to kind of breeze through it, you can use the trends. Okay, so we have CH3CO2H plus sodium and oxygen CH3. Okay, well, you have a sodium, and sodium's not really going to do anything except make this whole portion of the molecule negative. And you can see that from this, right? And here's a thing that you can do. Whenever you see a negative and you see like a hydrogen at the end point, well, that hydrogen really likes to bring positivity into the lives of molecules. And this molecule, you know, it just got laid off from work and it's pretty negative. But hydrogen, it wants to break off of this one and it wants to go to the negative portion and make it positive, make it neutral. So it makes you feel better. Okay, so whenever you see a sodium or any type of metal, that metal is going to be positive and it's going to make the other portion of the molecule negative. Okay, so we're just going to rewrite it. CH3CO2. Well, actually, we can write the reaction over here. We can do CH3CO2, and our sodium is going to be over here. It's still positive, and if this is positive and this molecule wanted to be neutral, what charge does this blue molecule need to be? Well, it needs to be negative, right? It needs to be negative because sodium is positive, and a positive and a negative is neutral, and this is neutral as well. Okay. All right. And now our hydrogen bonded with the is bonding with the negative molecule that was here. Let's go OCH3. And notice that since the hydrogen is positive, it's going to take away this negative sign. It's going to make it neutral. Alright, so that was our reaction. And we didn't have to do any Lewis structures. We didn't have to do anything like that. Just realize that when hydrogen sees a negative molecule, it's going to break off from its parent and go, and it's going to kind of bond over here. Or technically, technically it's like this. There's a negative, connects with hydrogen, but yeah. Anyways, just understand that this is how the reaction goes, right? And why this happens. Alright, so now comes the big idea, right? Which side is this reaction gonna prefer? Okay, well, you can say, yeah, there's pKa, and we just pick the pKa of the acids, and we'll do that, right? Well, it's not that simple. I mean, it is that simple, but it could be even simpler. Alright, cool. Let's figure out. We're gonna have to verify which one is acting as the acid and which one's acting as the base. Okay? Well, the acid typically in a Bronston-Lowry reaction, an acid donates a hydrogen, because for Bronston-Lowry reactions, you're dealing with hydrogens. But for Lewis acid-base reactions, you're dealing with electrons. For this case, we're dealing with hydrogens. So we're going to be doing Bronston-Lowry bases and acids. Okay. So which one is donating the hydrogen? Well, I see that this does not have a hydrogen anymore. So that must mean that this is going to be my acid. And since that was my acid, this has to be my what? This has to be my base, because it's the only thing left. Okay. And since this was the acid, whatever is the acid in one reaction becomes the opposite. It becomes the base. Right? Okay. And using that logic, whatever was a base in my reaction becomes the opposite in the other. It becomes the acid. This is a conjugate acid, and this is a conjugate base. Right? Conjugate base. Okay. Now here's the real kicker. Here's how I do these types of problems. Okay? Well, I actually compare my bases. I compare my bases when I'm doing this. Why? Well, first let me write out this reaction. I'm going to ignore the sodium because the sodium is just spectating. It's just an audience, right? You don't care about sodium. You just kind of ignore it when you're doing this. So OCH 3 negative versus CH3CO2 negative. Okay. So I just got my bases and I kind of put them over here. I didn't pick my acids. Why? Well, here's why. As the bases, well, okay, hold on. The more stable acid equals the weakest base. And the weakest base is preferred. Right? It's preferred. Now, why? Why is that preferred? Well, here's a silly little analogy that I made up. Whenever two Olympians have a child together, right? Let's say one Olympian is a weightlifter, the other one is a pole vaulter. So they're super muscular and they're super athletic and super built, right? They have abs and their abs have abs, right? And they sweat protein. Well, let's say that they have a baby. Is that baby, when it's born, going to be like super ripped and jacked and it's going to be like lifting weights and doing deadlifts, right? No. Two of the strong parents are going to make the weakest baby. If you cough on a baby, it's going to die. And it's super weak. So, naturally, we prefer to go to the weaker side. Right? And so, if I have a very stable acid, I'm going to have a super strong acid. But that super strong acid means that it's the weakest base. It is the weakest base. Okay. So what I'm trying to do is, I'm trying to get my bases and compare them. And the way I'm going to compare them is I'm going to say which one is the most stable acid. Which one is the more acidic acid. Because if it's an acidic acid, it's going to be the weakest base. And therefore, it is going to be preferred because I want the weakest base. Therefore, I want the strongest acid that I can get. Right? So let's see here. They're both oxygens, right? Right. So, since they're both oxygens, I can't just say, oh, electronegativity. No, I can't say that. Well, what can I do? It's better to write out the Lewis structure when you're not sure what to do. Notice I have a CH3, right? I have a CH3, so that means I'm going to have 3 hydrogens kind of piggybacking off of me. Okay? And there's going to be an oxygen. And that oxygen needs to be negative, so it has 1 bond. Let's calculate the formal charge really quickly. So 6 minus 6 electrons is 0. 0 minus 1 bond is negative. So indeed, that is negative. Okay. Let's write out the CH3, CO2. Right, so since I have a carbon with 3 hydrogens, I'm just going to have it structured like that. There's a carbon. This carbon right here is content. It has 4 bonds. And this this carbon is going to have an oxygen, right? And another oxygen. To make this carbon happy, I'm going to give it 4 bonds, right? So oxygen is going to be double bonded. That's a carbonyl, by the way, but carbonyl is not a functional group. Remember that if it's on the exam. So 2, 4, 6, and 8. And that's neutral. But notice that this oxygen only has 1 bond, so it becomes negative. Okay. Well, what do I do? you can say, oh, this one has, the most bonds. That means it's more acidic. Well, yeah, that's true. But you have to realize something, right? You have to realize something. This one is capable of doing resonance, right? It's capable of doing resonance. Let's blow up this section really quickly. Okay, so we have carbon attached to an oxygen that's negative, and we have a double bond with another oxygen. Okay, and we have some other bond to carbon. This lone pair of electrons can go over here and make a double bond. But that must mean that oxygen has to be like this, right? Because carbon can only have 4 bonds at a time. It cannot have 5. So when that new set of bonds come in, carbon has to shoot off some electrons somehow, or like transfer it, right? So that electron is going to be hanging out, and this is not here anymore, right? Okay, so that must mean that we have 2 structures. We have this structure that is possible, and we have this structure that is possible. Okay. Since we have 2 of the same structures possible, that increases our stability. If one of our forms don't work, we can, what? Go to the other form. We're more stable. If you have 2 jobs, right? Let's say you have 2 jobs. If one job isn't paying you enough, you can go to the other job. You are more stable. You are more financially stable, right? And so because we have 2 forms, this molecule is going to be more stable as an acid. A stabilized acid is a more acidic acid. And the more acidic acid is going to be the weakest base. And therefore, since this is more stable, I'm going to prefer it. Prefer, right? Yeah, so this is a preferred side. And you can actually see it. Normally, this is what I would do if I need to verify, like let's say I'm going back on the test, I finished, I'm going back on it, I'm going to review my answers. I'm like, hey, I was kind of iffy on this, I'm going to double check. I'm going to get my acids right here. I'm going to get my acids. I'm going to go over here, right? And we're going to say, oh, this is a carbonyl, or this is a carboxylic acid. It has a pKa of 4. And this is what? An alcohol. See an OH, the H is attached to an O. It's very easy to see an alcohol because in the formula, it has an H directly connected to the oxygen, and there's nothing else. So you can focus on that. It's an alcohol. And so alcohols tend to be 16. And realize that, hey, this is correct because when I do a reaction, I tend to favor the weakest acid overall, right? So we go from a very strong acid, 4, to a very weak acid, 16. And therefore, our answer is correct. The way I did it is that I compared my bases. The more stable base, or the most stable acid, is going to be, what? The weakest base. So really, I'm trying to find my weakest base. And then I can formulate an answer. And so really, this reaction is going to be, what? Product favored. Alright. I hope that helps. We're going to do a few more examples following this stepwise procedure, and I hope that you can understand what I'm doing. Okay, so like the previous problem, we're going to figure out what should we be expecting as our product, which one is going to be the preferred side, and which one is acting as our acid and base, and maybe, try to figure out the pKa as well, because I want you to know your pKa's. Very important on the exam, right? Okay, so notice that this sodium is what? Positively charged. If this molecule is neutral, then a positive has to cancel out a negative. So this is going to be a negative. The hydroxide is going to be negative. Very good. Okay. Well, again, you have this lone hydrogen right here attached to this carbon. And I guess you can pick this one too. But for our purposes, let's say it's the right one. And that hydrogen sees that this structure is going to be negative, and it's like, hey, I don't like that. I want to make you positive. And so it breaks off and joins with the other molecule. And so we have HC, triple bond, carbon, but that carbon now has some lone pairs, and it's going to be negative, right? Okay, so it's negative. That must mean that we're going to have a sodium over here. And notice that I don't connect them because really it's ionic. Ionic is kind of like this magnetism, you can say. It's going to have like this bond, but it's not really a bond to that carbon. So it's not connected, but it's like a magnet, right? If you understand that. So we don't connect them. It's an unequal sharing of electrons, right? So carbon is still technically negative. Sodium is positive, always. We now have that the hydrogen, let's make that pink, is connected to our water, or to our hydroxide. And you notice that this is actually water. Alright. So, you could also do this. I like showing it like this because it makes more sense about where it came from, how it occurred. Right? Okay, so now we label our acids, and now we label our base. It's more easy. It's easier to find your acids first, right? Because you're just losing a hydrogen. Whatever is on the other side has to be a base, right? Okay, so this one had a hydrogen, but it donated one, and now it doesn't have a hydrogen over here. That must mean that it's an acid, because acids donate their hydrogens. Alright, so that's an acid. And let's write that in red. This is an acid, because it donated a hydrogen. And by process of elimination, this is going to be my base. Okay. Whatever was an acid on the other side becomes a base on the other side. So this one becomes a base. And this one becomes a acid. Okay. Now, we're going to do my method. And my method is that we're going to compare our bases. And whenever you have a base, you're just going to ignore sodium. Just ignore it. So we're going to write out H, or OH, negative. So it's hydroxide. And we're going to compare it versus what? HC, negative C. Or it's triple bond, sorry, not negative. Okay, well, what do? I want to compare their acidity. That's right, their acidity. So which one is a good acid? You're like, I don't know. Well, what do? Well, you can use the trends. The more acidic molecule is going to have the most electronegative atom. And, I'd rather have the oxygen compared to the carbon. Because, remember that for electronegativity, we have N, O, F, we have Cl, Br, and iodine. And we increase our negativity going towards fluorine. Okay? So that must mean that oxygen is more electronegative than carbon. The more electronegative you are, the more acidic you become. Okay. So that must mean that oxygen is going to be favored compared to carbon. I don't want a negative carbon. Okay. So since this is the most acidic, that must mean it's going to be a weak base. And nature tends to favor the weak side. And so I'm going to say that this is, the preferred side. That's the preferred side. Now, if you're still having doubts, and maybe you completely believe me, maybe you just want to check over your work when you're, finished with your exam, I totally recommend it. Go over your pK. Okay. Well, let's see here. We're going to be comparing our acids, right? So this is a triple bond. And there's only carbons and hydrogens. That means it's going to be linear. That must mean that this is an sp hybridized. So what? Okay. Well, it's going to be what? 25 pKa. Compared to the other oxygen, compared to the other acid, this is what? An alcohol. So it turns out to be, actually this is water, sorry. This is water. So that's going to be 17. And you know what? 17 is more acidic. 17 is more closer to 0 than 25, right? 17 is going to be more acidic and therefore not favored. 25, however, is going to be more basic. It's more preferred. It's a weaker acid, right? And because it is a weaker acid, we prefer it. Nature tends to prefer the weaker stuff. And so we're going to go completely to this side of the reaction. Alright? Hope you understand that. We're going to do a few more practice problems. Okay, so step 1, we got to figure out what is going to be our product. Okay, instead of a sodium, we have a lithium. And it's exactly the same thing. This hydrogen is going to notice that this is a negative, and is going to want to try to bond with it. And because it bonds together, we're going to have a CH4, a methane. CH4. And we will also have a CH3, CH2O, negative, and then lithium, positive. Again, lithium is like the same thing as sodium. It's not going to be connected, but it is going to interact with this molecule and make it neutral. Okay? Now we have to realize which is our base, which one is our acid. It's easier to find your acids first, right? So which one out of these two donated a hydrogen? Well, this one donated a hydrogen. Therefore, it's going to be acting as an acid. And that must mean that the conjugate is going to be acting as a what? As a base. And I like my bases to be in blue. So, base. Okay. And what about the other one? Well, if this is an acid, then instinctively this one has to be the base, right? Okay. And because this was the base, whatever is a base on the other side has to be an acid on the other. So that's an acid. After that, we compare our bases. So CH3 minus versus, by the way, I'm ignoring lithium. It's a metal. Just ignore it. It's a spectator ion. Right? So CH3 versus CH3. CH3. CH2. O negative. Okay. And again, hey, this is more of an electronegativity. Sometimes you don't even have to draw your Lewis structure. Sometimes you could just look at the molecule. One molecule has carbons and hydrogens. The other one has an oxygen. And that oxygen is more electronegative because it's closer to fluorine than carbon is, right? And because it's more electronegative, it's going to be the more stable acid because it's more acidic. And the more stable acid, the more stable an acid is, the weaker the base. And since this is a weaker base, we tend to prefer it. Nature tends to prefer the weaker side. Therefore, we can say strongly that this side is preferred. Okay? But let's verify our findings. If you're not so sure, you can draw a Lewis structure of this. You can actually you can actually find the Lewis structure. You can do CH3 with a C and then an alcohol. That right here is an OH group. It's an alcohol. Okay, since this is an alcohol, we're comparing our acids, by the way. The pKa for an alcohol is going to be 16, right? And you can remember that because liquor tends to be like water. It has some water component in it. And water is like 15.7, so it's very close to water. But it's a little bit more basic than water. Okay. And now we're going to be comparing our, what? Our other acid, CH4, methane. Well, there are 4 things surrounding our carbon, and there's only hydrogens. So we're not going to be using electronegativity because C and H, they're almost the same thing. They're nonpolar. So the only thing that I know how to do with carbon and hydrogen is, well, sp trends. There are 4 things surrounding us. Therefore, we have an sp3. And when we have an sp3, we only have 25% S character. And that is the lowest S character possible, right? So that must mean that we are not a very good acid. We're not very good. In fact, the SP character, or this pKa, is going to be 50. It's super, super weak. That means it's a very good base. And because this is more acidic than this one, 16 is more stronger than 15, we're going to prefer the 50 side. Excuse me, 50. We're going to prefer the 50 side. And therefore, we're for sure going to go to the right direction. Because reactions tend to favor the weakest base. Right? And one side, this side, is going to have the weakest base and the weakest acid. You're not going to find the weakest base over here and then the weakest acid over there. No. The weakest base and the weakest acid are always going to be on the same side. If a question is given to you on an exam like that, you should know it. The weakest acid and the weakest base are going to be found on the same side. Always. And so now you try to do this problem on your own. Okay. Well, realize that CH3 was negative, and now on the other side, CH3 became CH4. That must mean that we accepted a hydrogen. And that means that we are, in fact, a base. And since this is acting as a base, this one is going to be the acid. This is the acid. And whatever is the acid on one side has to be a base on the other. And whatever was a base on the other side has to be an acid. Okay. And now we compare our bases. CH3 minus versus this right here. Okay, so which one is going to be preferred? Well, again, you look at your oxygen and you're like, hey, this is more electronegative. And the more electronegative I am, the more acidic I become. And the more acidic I become, the weaker the base I am. So the stronger the acid, the weaker the base. And therefore, since it is a weak base, it's going to be preferred, because nature prefers the weaker side. And so we're going to say it is this side that we are favoring the product side. Okay, so that was pretty easy, right? Hopefully you can do that on more practice problems that you find online or in the book. Alright, so which one is going to be preferred? Is it going to be the left side or the right side? Alright, well, we're going to have to realize which one is our acid and which one is our base. We had an H2O, on the other side we have an OH. We lost a hydrogen. That must mean that we are acting as a base. That must mean that this is an acid over here. So this is a base. And these are going to be acids. Or, oh, I'm sorry. I'm sorry. My apologies. So this is acting as an acid because we lost our hydrogen. It's best not to rush on this. And that must mean that this is going to be a base right here. Okay. And because that one's a base, this one is going to be an acid. And because that one's an acid, this one has to be a base. Yeah. Don't rush. Okay. My apologies. I'm sorry. Now we compare our bases. We're going to be comparing bases. Versus what? OH. Well, they're both negative. Well, they're both electronegative, and they're both oxygen, so what do I do? Well, I say that we prefer the one that has resonance, right? Resonance. So this negative electron, or these electrons can go over here, form a double bond, right? With this oxygen, and then that double bond has to move up. And so our negative sign goes over there. Because we have two forms, we're technically more stable than this alcohol group, this hydroxide. And because we're more stable, we're going to be a better acid. Because we are a better acid, we're going to be the weaker base. And because we are the weaker base, we are going to be preferred, right? And for verification, let's see here. By the way, it's going to go over here. Right? For verification, let's try to check it out. Our acid is water, so we have 17. Our acid over here is going to be a carboxylic acid. That's a 4. Right? And 17 is going to be weaker than 4. 17 is higher up. 4 is going to be super acidic. It's not that acidic, kind of, but it's like really acidic. So it's going to be not as favored. 17 is really not that good. and is going to be favored because it's not a good acid. So 17 is better than 4. We're going to proceed to the left. Again, this trick right here is if you're trying to rush, right? And then straight up PKA when you're trying to review back before you turn in your test. So again, I highly recommend that you set your PKA, that you use the trends, understand what's going on. You have electronegativity that affects things, right? So oxygen is more electronegative than nitrogen, more electronegative than carbon. Fluorine is going to be super electronegative, it's going to be super acidic. Then you're going to have your bonds, right? Well, actually, it's electronegativity. Let's call that En. Then your resonance, and then your bonds. So if two things do not have resonance, the one with the most bonds is going to be more stable. And electronegativity is first, resonance is second, bonds third, right? The more resonance you have, the more stable you are. The more electronegative you are, the more stable, the more acidic you become. So I hope this helps you. I hope this kind of alleviates some of the pain from acid-base reactions. And I hope you do amazing on your next exam. Thank you for watching.